Okay, so this is kind of where we ended, was doing all the math for the light problems, and that was your assignment over the weekend, was to do some reading and do the math that's associated with it. For the math problems, there's really only two equations. There's the speed of light, that's C equation, equals wavelength times frequency. And then there's the energy equation, which is E equals Planck's constant times frequency. And then you just plug numbers in. C is a number, H is a constant. Again, you don't have to memorize them, but I'll give them to you. But you do not need to know how to use the equations. And then again, we kind of discussed that the equations both have frequency in common. So if they give you like wavelength and they want energy, you would use the C equation to solve for frequency. You'd use wavelength and C, because C is this number down here. And then you would solve for frequency, and then you'd plug the frequency in down here and use it with Planck's constant to get energy. So it would be like a multi-step problem. So that's kind of where we finished up. So now we're going to talk about light. So we talked about light as waves. Hold on one second. Okay, so all forms of electromagnetic radiation move at the speed of light, which is this number, in a vacuum. That means there's no, a vacuum is like a sealed container where there's no like resistance or anything, which would not be like what we're sitting in right now, right? We're not sitting in a vacuum with no air resistance. And so the equation for light as a wave is this one. Well, why? Well, because this symbol right here means wavelength. So this is why the equation that does mathematically discussing light acting like a wave and traveling through space like a wave. Okay. So if you did the reading, you'll learn about the photoelectric effect, which discovered that light behaves two ways. It doesn't just behave like a wave, it also can behave like a particle. And they did this was a discovery, how they saw these emissions of electrons, which are photons, also called photons, which are just particles of light, or which are just made up of electrons that have energy. And the emission of the electrons when they were shining light on the metal meant that the light was not traveling like waves, it was traveling like a particle. So then they came up with this, it's called the quantum mechanical theory model of the atom, and that is really what we do use today, okay? So the word quantum in this class just means energy, okay? Energy that can be gained or lost by an atom. So this equation, even though we did it already, is the equation for the energy of light when it behaves like a particle, okay? And then energy again was measured in joules, or it can also be in kilojoules per photon, per one individual particle, okay? So we see a bunch of so these are like fireworks. So this is light being given off, right? So you provide energy and then they kind of burst into these beautiful colors. Well, most of these colors are made up of chemicals. So elements can when provided energy, can give off different forms of radiation. And when I say radiation, I'm not talking about necessarily always dangerous radiation, right? Visible light is a form of radiation. It's called electromagnetic radiation spectrum. So it's not harmful radiation, but visible light is. And there are lots of metals that actually burn beautiful colors. They give off beautiful colors. And that has everything to do with how the electrons are excited and then released in an atom. And so that's what we're going to kind of go into today, okay? So the Bohr model of the hydrogen atom we are going to use for simplicity's sake. It will help us understand the model better. It is not the true model of the atom anymore. This was like the original model of how they thought electrons were organized. And yes, we will use it and talk about it, but truly it is a lot more complicated than this. So the Bohr model is like kind of like a simplistic model of how Niels Bohr was a scientist and how he thought electrons were arranged. So you're going to have to get used to some vocab in this part of the chapter. So we're going to have to get used to some vocab. So the ground state, or the ground state energy, is the lowest energy level. So this little n right here, you want to mark on this. This tells you what Oh, of course I can't write on this one. This tells you what energy level you're on, aka what ring of the atom you're on. And again, we'll use these words a lot today, so hopefully you don't have to like necessarily memorize it. You'll probably get used to them, okay? An excited state for an electron is when an electron is on an energy level that's further away from the nucleus, or like a further ring away from the nucleus where it wouldn't be normally. Okay, now, so electrons can be excited, meaning usually energy is put in and they jump to these higher energy levels. Well, if they do that and they're in the excited state, generally they're not very stable there. They're happier in their ground state or more stable in their ground state. So what they will do is they will end up falling back down to their ground state. That is when the energy is released, right? Law of conservation of energy says either energy can't be created nor destroyed. It has to be like rearranged. So if you put energy in to something, energy is going to have to come back out, right? It doesn't just like disappear anywhere. So when the energy is released in a form of radiation, some type of electromagnetic radiation, a particle called a photon is emitted. Now, if that form of radiation has energy that is in the visible light spectrum, we will be able to see that in the form of colors of light. Now, if it is not in the visible spectrum, we won't see it because, right, we can only see a small part of our radiation spectrum. Now, this can happen with things like uranium. So uranium has been used in chemical warfare because when it's excited, it'll end up releasing energy in the form of gamma radiation. And you can't see it, but it is super, super harmful, high energy, and they've used it to injure and kill people, really, in essence. So this is all this concept of any atoms, hydrogen, lithium, helium, uranium, whatever, they can absorb energy and then release it in the form of light. And again, light isn't always visible light. Gamma rays are a form of light. X-rays are a form of light. It's just a different word for radiation, okay? And again, radiation doesn't always mean bad. Microwaves are a form of radiation, but it's not a form of radiation that's going to hurt you. They're fairly low energy. They have really long wavelengths. So let's keep going, okay? So Bohr's model only worked for hydrogen. So his model of the atom only worked for an element that had one electron, which is hydrogen, and it has what's called unique spectral lines. So the problem is the Bohr model didn't explain any other element but hydrogen, or how elements or atoms were behaving chemically. However, we're still going to use it for the sake of simplicity. Okay, so we're going to talk about it. So here's the Bohr model of the hydrogen atom. Here's the nucleus, okay? And the Bohr model is probably one that you've seen before. They generally teach this in like, middle school, where you draw the nucleus in the center and then you draw rings around them. These rings are called energy levels, and they're also represented by the letter N. N means energy level, or you can also, a fancy word is called, let me go to my colored. A fancy word that you might see written around can be called N is quantum, or energy level. And this is just these rings where Bohr thought the electrons were located on. Now for hydrogen is atomic number 1, which means it has 1 proton and 1 electron, right? If it's assuming it's neutral, 1 proton, 1 electron, okay? And so so here's the nucleus with 1 proton in it, and then he thought these electrons, so there's 1 electron on my first energy level. This is called the ground state model, Bohr model of the hydrogen atom. The ground state because the electrons will always want to go into the lowest energy level first before they start reaching out to the outer energy levels. So this would be a ground state version of the Bohr model atom of hydrogen. Now, if I were to do this, and I have +1 in my nucleus, it means it's hydrogen, and I have my 1 electron on this second ring, n equals 2, second energy level. Anybody know what this would be called in terms of the hydrogen atom? What kind of hydrogen atom is this? So it's not a ground state because it's not in the lowest energy level. I've moved it to a higher energy level, the second energy level. This would be called a depiction, thank you, Luke, of the excited state. This would be an excited state version. It's still hydrogen, right? There's still 1 proton in the nucleus, but the electron is not in its lowest state, so this would be called an excited state. So again, we're going to use these words a lot today, and we're going to do lots of different demonstrations. Okay, so I'm going to talk about this later, but line emission spectrum is when electrons get excited, and they usually get excited by adding, oh, that's why, no wonder. They usually get excited by adding energy. Now, in real life, how do you think we excite electrons? Well, there's 2 pretty common ways in real life that we excite electrons. How do we provide energy to electrons? Like, how do we get electricity? What do we do? How do you get electricity in your light bulbs or your lamps? You guys could unmute yourself. Right? You plug them in, right? That's putting in energy, right? You're providing electricity to put in energy. Anybody know another way we can excite electrons in an atom? Like by adding energy besides electricity? So electricity is one way. It provides energy. Anybody know another way? What do they do to fireworks? What do you do to fireworks?
Light them.
Yeah, you light them, which is also providing heat. Okay, so adding energy, so that's like in the form of electricity or heat. So that's how they do fireworks. Now, when you see the beautiful colors of fireworks, it is not because you're providing energy. It's because you've provided energy. The electrons become super unstable in the excited states, and they fall back down to their original energy level. That is when you see photons, which are just particles of light being released, and if they're the right energy, they'll be released in the visual part of the spectrum, and you can actually see it, okay? Now here's something cool, is every single element, lithium, sodium, potassium, chlorine, zinc, carbon, uranium, hydrogen, every single element's emission spectrum is unique. It's like its own fingerprint. They often refer to it as like a fingerprint. And the reason that is because every single element's electrons are arranged in a specific manner that is unique to that element. Every element, neutral, we're talking about neutral elements, have a different number of electrons. And because it has a different number of electrons, they're arranged differently. And because they're arranged differently, how they emit light or radiation is different for every single element. Okay? So, pretty much the Bohr model of the atom was a great way to talk simply about atoms, but the Heisenberg uncertainty, the quantum model of the atom included the Heisenberg uncertainty principle, pretty much saying that in physics, it's pretty much impossible to know exactly the speed and position, location of a particle, aka an electron, simultaneously. Like you can't know both because the second you would find it, it would move, right? So this idea of the Bohr model, like right with these just like rings around the nucleus, where these electrons were just in fixed positions, became outdated. I mean, it's okay to use it, and we are going to use it just for simplicity's sake, but it isn't really this simple. It's actually a lot more complicated, and so they call this the quantum model of the atom instead of the Bohr model. So what does the quantum model of the atom consist of? Well, it consists of what they then called atomic orbitals. And these orbitals were regions in the atom where you had a good chance of finding the electron. Like they were probably there most of the time, okay? Electrons are constantly moving, so it's impossible that the second you locate it, it will move again. So it was really, really more complicating than thinking they just orbited around the nucleus in circles. It's not that simple. So again, remember this little n, we talked about this little n is what energy level, aka in the Bohr model, this is what ring you're on in the Bohr model, okay? Now, it is very, very, very complicated math. It's called Schrodinger's equation, and he pretty much discovered, he was able to use some mapping and discovered these orbitals where the electrons were constantly being found over periods of time. And he found out that these orbitals actually ended up having like shapes. They're not just like these, perfect little rings around the nucleus. So it's the atom is just a lot more complicated than Bohr's model. Okay, we're going to reference Bohr's model because it's going to make life easier, but it is really a lot more complicated. So let's talk about orbitals. So if you don't have your periodic table out, please get it out. I'm going to give you a minute because I really do want you to have it out. So I'm going to give you a minute and pause. Have your periodic table out. You're going to need it all the rest of the day today. Okay. So your first two families on your periodic table are considered your S block. This is where you're going to find what are going to soon be called S orbitals. Okay? And now I realize that, so some periodic tables have hydrogen and helium over here. Most of them have hydrogen over here and helium over here. Helium is an S block element. It technically has 2 electrons, so 1, 2. So the reason it's over here is because it has a full valence shell, like it's noble, all the other noble gases. So it is a noble gas, but it's an S block element. Okay. So all your transition metals, that's right here, are your D block elements, okay? All these elements right here after your transition metals all the way over to your noble gases are your P block elements, and then your lanthanide and actinide series down here are called F block. This is not going to mean anything to you until we start doing this. So you're kind of just going to have to listen, and then when we do practice, it will hopefully make more sense. Right now, it probably makes 0 sense, and that's okay. I just need you to know this, and then we're going to kind of build on it. Okay, so atomic orbitals. So this is an arrangement of electrons around an atom, and then we're going to call this electron configuration. It's these locations where we're finding electrons. So there's 3 ways to do it. The first way is the first way we're going to do, orbital notation. This is showing electrons in different regions around the atom. And then electron configuration just takes that and writes it out in numbers and letters. And then noble gas notation is like your shortcut method. So we're going to do noble gas notation last. Okay, so let's look at the Bohr model. I know it's not truly the correct model, but let's look at the Bohr model of the nitrogen atom. Do you remember from like middle school how they did the rings? Do you remember how many electrons could go in each ring of the Bohr model? Does anybody remember? So it's 2 in the first ring, okay, but then it's 8, okay, and then 8, and then 18, and then it kept going, okay? So let's find nitrogen on our periodic table. Sorry, I'm trying to pull up my periodic table. All right, nitrogen is atomic number 7, and as long as it's neutral, it will have 7 electrons. So I'm going to fill in the Bohr model of the atom. I get to put 2 electrons that are going to be these little circles on my first ring. There would be 7 positive charges in the nucleus, right? Because there's 7 protons. So 1, 2 electrons, and then 3, 4, 5, 6, 7, 8. Oops. Whoa. Undo the last one. There's only 7, sorry. So there's 1, 2, 3, 4, 5 electrons in the outermost region. We're going to call this the valence shell down the road. Okay, and in the inner shell electrons, there's 2, this one and this one. This is an inner shell. It's inside. This one's on the outside. That one's going to be called the valence shell. Okay, so this would be the Bohr model of the atom, and he thought these electrons kind of just rotated around the nucleus, kind of like all the planets move around the sun, and they sort of do, but just in a little bit more complicated fashion. So let's talk about this. This is really what the Bohr model looks like. So here's your nucleus right here. Okay, this gray sphere is called an orbital. This blue, hello. This blue sphere is also an orbital, and then these guys that look like they call them the dumbbell shape. This purple is a dumbbell, that's an orbital. This yellow one is another orbital, and this blue one is another orbital. So obviously this is much more complex than we imagine. It isn't just these beautiful like little rings. Okay, this is more of what it really looks like. So we're going to go into more about the orbitals in the quantum mechanical model, okay? So your s orbitals, which start, in your s block, okay, on your periodic table. They start on the first energy level. That means n equals 1, okay? And the reason they call them s orbitals is because they're spherically shaped. They're spherically shaped. That's where they got the S from. Hold on, I gotta let a couple people in. They've been getting kicked out. Okay, there's only one way to draw a sphere. A sphere is a sphere is a sphere. It just, as the atoms gain more electrons, the spheres just get bigger. So this would be on energy level 1, s orbital. This would be on your second energy level, s orbital. This would be like a third energy level, s orbital. Because as an atom gets more and more electrons, the atom gets bigger and bigger and bigger. Okay? So that's your s orbitals. They're spherically shaped. Okay? P orbitals are referred to as dumbbells. They kind of look like two little lobes. And they are based on axes. Now in 3 dimensions of space, right, you have your x-axis, your y-axis, and then I know this is hard to draw, but z would go push out at you and go backwards. This would be your z-axis. So a px orbital would look like this. Okay? And it would lie along the x-axis. This whole thing is a px orbital. Okay? Now, so a py orbital would look like this. This is the y-axis. So it kind of looks like a figure 8. Again, they call it dumbbell shape, so you need to know this one. This is what it's generally referred to. So this would be a py orbital. Again, these are regions that they're finding electrons in at any given moment. Okay? Which then means a pz orbital would lie along the z-axis. So again, they're all the same shape, they're just oriented in space along different axes. Now, the p orbitals don't start till the second energy level, n equals 2. Let's look at our periodic table. If you go back here, this is your first energy level, or first row, or first period, or n equals 1, okay? It's like this is n equals 1, this whole row. Right here, this is n equals 2. It's your second row, or second period, or second ring, or whatever you want to call it. So notice your p block, which is green, doesn't even start on the first energy level. So you don't start seeing the p orbitals until the second energy level. Okay, so there's still s orbitals, but now there's also p orbitals on the second energy level. Okay, so s, p. Now, d is crazy. D orbitals are very complicated. Most of them look like 4-leaf clovers rotated along the different axes. And then there's this really random little guy that's just looks totally different. It looks like a donut with something shoved in the middle of it. So this is like a weird one. But look, there's 1, 2, 3, for 5 different shapes, 5 different regions where electrons can be. So 5 different shapes. And generally they do call it the 4-leaf clover, even though this one does not look like a 4-leaf clover, because the majority of the orbitals do look like 4-leaf clovers. This is where things get tricky. If you look at your D block, I wish I could draw this. So this is S, so D is right here. D starts where your transition metals start, right? D right here. What's tricky about the D block, let me see, I'll go back to the original one, is that it looks like it starts on the 3rd or the 4th energy level. Hey, why is it doing that? So your D block looks like it starts on the 4th energy level, but it doesn't. What they did when they built the periodic table was they dropped the D block down in to make the periodic table look better. Okay, so here's something that is tricky. Why is this not working? I need you to just remember, hopefully this will eventually end up loading. That even though this is 4, whoa, it restarted everything, okay. That even though this is 4S right here, this row right here is not 4D. I need you to call it 3D. And then this is 4D. And this is 5D. And this is 6D. So the D block is always going to be 1 energy level behind the S block. And then it goes back to normal. So this is 4S, this is 3D, this is still the 4th energy level. The P block is normal. This is 4P. It's just the D right now that's funky. It's always 1 behind the S. Okay? Now, again, this is probably not going to make much sense till we start filling in electrons. Okay? I just need you to kind of bear with me through this. Our final energy, or our final orbital, are called the F orbitals. They're super duper 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 complicated. And they start on the 4th energy level. So S starts on the 1st, P starts on the 2nd, D starts on the 3rd, F starts on the 4th. And there's actually 7 shapes. So these are the 3 funky ones. Okay, and then the 4 other ones are like these 8 lobes. They kind of look like flowers, but they have like 8 lobes, right? So 4 on top and 4 on bottom and 4 out and 4 back and 4 left and 4 right and so forth, all rotated around the X, Y, and Z axes, okay? But you should start to notice a pattern here, okay? So these guys start at the 4th energy level, which is even more confusing, right? Because if you go look at your periodic table, I show the F block all the way down here, right? So this is called 4F, and this is called 5F. This row is 4F, and this row is 5F. So the F block is 1 behind the D block, and the D block is 1 behind the S block, okay? So I'm going to pull up real quick your periodic table, just real quick. Give me 1 second. Okay, so if you look at this, you guys can see this, right? Yes, please. Oh, I can draw on this, yes. Okay, okay, thank you. So if you look at this, you will see how the periodic table is arranged is super funky. Look, so it goes 6S, this is 6S right here, this whole area, okay? Remember the D block right here, this right here is your D block, this whole thing right here. This would be 5D. Remember the D block is 1 behind the S. Now look at 55, 56, 57. this is drops down. 58 is right here. So 57, 58. So it continues down into the F block before it goes back. So 55 or 57, 58, 59, 60, blah, 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 71. And then it goes back to 72. So really this F block should be thrown into here. Okay, this F block should have been right here, but to make the periodic table look nicer, they dropped it down here. This is all just for ease and looks, okay? So this is 4F, which means this is 7S. This right here is going to be 6D, and this is 89. 90 is right here. So this is 5F, 4F, 5F. So the F is 1 behind the D and 2 behind the S. 6S, 5D, 4F. Again, this is going to make more sense when we start filling in electrons, okay? So let's see. Let's get back to my notes. Okay, we're going to start filling in electrons, and there are rules to follow or to fill in the electrons. The first rule is you're always going to put electrons in the lowest energy level first. So the lowest principal quantum number. So that's like the first ring. Always put them in the first ring first. So that's called the off-bow principle. Okay, the Pauli exclusion principle says you can only put 2 electrons in an orbital, and they have to be spinning opposite directions because electrons really don't like other electrons. Electrons, right, repel other electrons. So if you're going to put them next to each other, they need to be spinning opposite ways. That's represented by an up arrow and a down arrow. Now, when I do these, I'm going to do like half arrows. So I'm going to just show you what mine end up looking like. This is like my up arrow. You're welcome to do a full arrow. This is my down arrow. It's how I've always learned it, so that's why I do it. But you are welcome to do a full arrow, okay? It doesn't matter. It's not a big deal. These mean the same thing. Again, they're spinning opposite directions. Otherwise, they would repel each other and fly off the atom. So that's this principle right here. Now, this is the harder one. Hund's rule states that when you have multiple orbitals to put electrons in, you won't pair electrons up until you have to. So like if I'm putting electrons in, I would go like this. And then I can max out my orbitals. The reason this is electrons don't like to be next to each other. They will space themselves out as far away as possible from one another before they go next to each other. Okay? Again, these will make more sense once we start practicing. So here we go. We're going to practice now. Okay, some wording that I'm going to use is on this slide. I'm going to talk about highest occupied energy level. I'm going to talk about valence electrons. Those are the electrons in the outermost ring or outermost energy level. And the reason why they are so important is those are the electrons when we get further into the year that are the ones that are involved in bonding and chemical reactions. So they're super important to understand. And then the inner shell electrons are just any electrons that are not in the valence shell. Every other electron closer to the nucleus. Okay. So again, I'm going to use these words a lot today, so you'll probably get used to them. Okay. So this is phosphorus. Now let's go back to our periodic table. I want to read it. Oops, I'm going to go back to, so I want you to follow along with me. Let me clear this. I wonder if I could, no, whatever. So I just want to, why is my, oh, sorry, I was using the wrong part of my pen. I was like, why is my pen not working? So we're going to just read the periodic table like a book. I want you to read it with me. So this is energy level 1, why it's on row 1. That's why. So this is 1. What block is this? This is the S block. So this is 1S. Okay. What energy level are we on? 2. What block is this? S. So these are 2S, both of these. Then we keep reading like a book. What energy level are we on? 2, right? We're still on the second row. What block is this? I'll wait. Anybody? P. So these are all 2p elements. All of them 2p. Okay, what row are we on? 3. What block is this? S. So these are 3s elements. Keep reading the book. What row are we on? 3. What block is this? P. Okay, what row are we on? We're on the 4th. What block is this right here? S. Right, this whole, your alkaline metals and alkaline earth metals are S block elements. Okay, careful. I know we're on row 4, but what block is this and what do we call this whole row? This is the D block, right? Okay, 3D, good. So this is the D block, but remember the D block starts on the 3rd energy level. I know it does not line up. That's why you just have to be very careful. We call this 3D. All of these elements are 3D. All right? Then we go back to normal. This is, our P block is lined up with the S block. So these are all 4P elements, all of them. Okay, keep reading. Energy level 5, so this is 5S. Okay, what is this called? If this is 3D, this is 4D. Okay, then we go back to normal. This is 5P. Okay, 6S right here. These are D block elements that I have. This is called 5D. I'll drop down in just a second. This is normal, so this is 6P. The S and the P will always match if you're in the same row. So, but 6S, 5D, but remember, this drops down to here. This is called 4F, this whole row. Remember, F orbitals start on the 4th row. They've just dropped them down to make the periodic table look better, okay? So this is 7S, which makes this 6D. And in fact, they actually have more of these filled in now. They're all man-made, but they do have more of them filled in now. So 6S, now if this is 7 and this is 6, this is 5F. And this is kind of how the periodic table goes when we're throwing in electrons. This is small, this is big. Think about it as rings. This is a 1 ring, 2 ring, 3 ring, 4 ring, 5 ring, 6 ring, 7 ring. 7 rings, like your atoms start to get really big. Look how many electrons this guy's gonna have. Like, right, francium has 87 electrons we would have to fill in. So they get bigger and bigger and bigger, okay? Now, let's look at the question we're gonna do is phosphorus. Okay, so phosphorus. So you go to phosphorus on your periodic table. I have it on my slide. Okay, phosphorus is atomic number 15. So what does that mean? That means it has 15 protons, and it also means it has 15 electrons, assuming that it's neutral. So here are, if you just followed with me reading the periodic table, this is the order that the orbitals go in terms of energy, okay? As you get further and further away from the nucleus, those electrons have more and more energy, okay? Now, so this is like the 1st ring, okay? This is like the 2nd ring. I'm only doing half rings, okay? 3rd ring, 4th ring, and so forth, right? Where my nucleus would be here, and we're filling in electrons around the nucleus. I'm just doing half rings, okay? I'm not doing like a full circle. Okay, so it really wasn't just as easy as being like, oh, put 1 electron here, put a bunch of dots here. They're actually in these different shapes or locations. So how do we do this? Well, if I have 15 electrons I have to work with, I have to fill them in. Now, Hund's rule states that I have to put them in the lowest energy level first. I'm sorry, that's the off-bow principle, my bad. So I can put 1. How many maxes out in each orbital? 2, right? And they have to spin opposite directions. I've just accounted for 2 electrons. So 1, 2, okay? I maxed out at 2 electrons. Now, why are there 3 boxes for the P's? This is super important. Look at all your P orbitals. Every single 2P, 3P, 4P, 5P, 6P, every single one of them has 3 boxes. Why are there 3 boxes?
Is it because they have 3 different shapes?
It is. Very good. It's because they have 3 different shapes. There's PX, PY, PZ. PX, PY, PZ. PX, PY, PZ. PX, PY, PZ. Okay? So having said that, why do all of these Ds, 3D, 4D, 5D, 6D, why are there 5 boxes? Well, because there's 5 orbitals, right? There's 5 different shapes, 5 orbitals, and really orbitals are shapes, 5 shapes. Okay, and then the F has 1, 2, 3, 4, 5, 6, 7 because there are 7 orbitals for F, or 7 shapes. That's 7 different possible locations you could find an electron at any given time. Okay, so let's finish phosphorus. This is the orbital notation. I guess I should write that. Orbital notation for phosphorus. We're finishing it. So far, I only have 4 electrons, so I'm not done. Now, if I go to fill these in these, do I do this first? What rule states that this is wrong? It's Hund's rule, okay? So, Hund's rule is, I'm going to go back. You put them in one by one before you pair them up. And these, again, these lines are electrons. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I need 15, right? It's atomic number 15, so I need 15. So I'm going to keep going. Fill this in. 1, 2. Now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Is this correct? I'm going to tell you this is wrong. Why is this wrong? You do not pair electrons up until you absolutely have to. They do not want to be next to each other. So this is 2, 4, 6, 8, 10, 12, 13, 14, 15 electrons. This is the orbital notation for phosphorus. So let's talk about some vocab. I'm going to refill this in so it's less messy now without all those other words on it. Let's talk about vocab. The highest occupied, energy level. Highest occupied energy level is N equals 3. This third row, this would be like your third ring. Yes, they're separate orbitals because p orbitals are slightly higher in energy, but if I were to draw my third ring, this is my third ring and this is also on my third ring, your highest occupied energy level is N, which means energy level, or rho, if you want to go for that, is 3. Okay? So how many valence electrons, VE, valence electrons, are there? Well, this is my highest occupied energy level, and so is this. So I have 1, 2, 3, 4, 5. Phosphorus has 5 valence electrons, which makes all of these guys right here inner shell electrons. Okay, these are all inner shell electrons. This is my only valence electrons. Okay, 5. Questions so far? What if I do this? What if I take that one electron that was right here and I put it here? Now this still has 15 electrons, right? So assuming it's neutral, it's still phosphorus, right? What is this called? Well, actually, let's go back. Give me one more second. Let's go back. This would be called ground state orbital notation for phosphorus. Everything filled in the right way. Now, if I take this like electron that should be here and I throw it up here, what would this be called for phosphorus? This would be called an what? Excited state. okay? Because this electron is not where it's supposed to be. It's in a higher energy level than it's supposed to be. How would something like this happen? How would you get like an electron to jump up here? Well, you would put in energy, like heat it up, okay? Or put in electricity, okay? That's how you can get these electrons to have more energy and jump up to higher energy levels, which would then be called excited states, okay? Again, they won't stay there. They'll end up falling back down and releasing the energy that they originally absorbed, but this can happen by exciting the atom. Okay, so these slides just show me filling in the electrons like I just did. Okay, now here's what's cool about this is we can go back and you can read what you've done. So I'm going to go back to my drawing, and electron configuration, okay, so this is orbital notation. Electron configuration is just you reading, sorry, my pen is delayed. It's just you reading this. So electron configuration is going to be this. 1s, so it's kind of like a map of where the electrons are. I'm on the first energy level, I'm in the s orbital. How many electrons? 2. You write that as an exponent. Keep reading. What's next? 2s. How many electrons in there? 2. The next orbital is 2p. How many electrons in there? 2, 4, 6. 6. Keep reading. 3s. How many electrons in there? 2. The next one, 3p. Sorry, you kind of can't see that 2 right here. 3p. Okay, how many electrons are in there? 1, 2, 3. 3. So this, right, so this is orbital notation. This is electron configuration. So that's what the second one was, right? We had orbital notation, electron configuration, and then we will do noble gas notation. Now, here's the cool thing, is you don't need orbital notation to do electron configurations. All you really need is the P table. You need to know what block they are. So, let's go back to my periodic table. Okay. I wonder if it'll let me open a new one. I'm trying to... I'll just do this. All right, look at phosphorus. It is located right here. And to do its electron configuration, all you have to do is read the periodic table like a book until you get to phosphorus. So I'm on my first energy level. So 1, what block is this? S. I count across 1, 2, 2. Now I'm at helium. I'm not at phosphorus yet, so I have to keep going. Energy level, what's that? 2. What block is this? S. How many electrons? 1, 2. Keep reading your periodic table. What energy level? 2. What block is this? P. This is the P block over here. Keep counting. 1, 2, 3, 4, 5, 6. Now I'm at neon, so 2p, 6. I'm not finished. I have not gotten to phosphorus yet. Keep going. 3. What block is this? S. 1, 2. Now I'm at magnesium. So like this is the electron configuration for magnesium. But I don't want magnesium. I want phosphorus. So I keep reading. What block is, or what energy level? This is still 3. What block is this? P, right? And then I count until I get to phosphorus. 1, 2, 3. There's the electron configuration using the periodic table instead of orbital notation for filling it out. So what I would like you to do is take a minute. I'm going to upload an orbital notation. So I'm going to pause this real quick.